record and jump in there. Okay, so hello everybody. Welcome. You've just had your second test. There is only two more unit tests and a final exam. If you want to know when everything's coming up, we are going to be doing chapter 7 today. We'll be doing chapter 8 on the 1st and chapter 9 on the 2nd. And then we will be doing the test for 7, 8, 9 this Friday. So pretty simple. Then next week we will be doing 10 on the 6th, 11 on the 7th, and 12 on the 8th. We'll then be doing the test for that on the 9th. And then on the 10th, which is the last day of this first semester class, we will take the final exam. So that's your next couple days. Since we're at the halfway point, what's coming up? You got a test on the 3rd, you got a test on the 9th, and then your final is on 10th. And then every single day you'll have some assignment that gives you credit. Today's assignment is a quiz. Tomorrow is a quiz, but on Thursday, I'm probably going to have you do something written because that's naming, and naming can be difficult. So a quiz multiple choice is probably not as helpful as you doing actual like piece of worksheet or whatever. So let's get into chemical bonding. Before we do that, just some quick bits of news. We're going to stay on this CHS Canvas, so you don't have to worry about that. And you may have gotten an invite for the second semester Canvas class. As you can see, it's right down there. I haven't published anything on it yet, but the second semester will also be on Canvas. So if you're here and you're paying attention, then you're good to go. No need to worry. And then the test you guys did pretty good. I think the overall is like a B. Let's take a look at it. All right, there it goes. So yeah, average score 87, almost an A, so that's pretty good. There were some issues with this test for some reason when it was doing, it has it to where it randomizes the answers, and so sometimes it would randomize it and it would put it on there twice, and so I had to fix that. But if that happened to you, then I went through and made sure you had the right points, and I knew that was taking place because it shows me the statistics on the question, and all of a sudden you could see like, oh, okay, instead of it just saying AMU here, I would run the statistics and it would say AMU twice or whatever. And that was a weird Canvas thing of, this test could have been, something else, but I'm using Canvas so it auto grades it for you. But unfortunately it was hitting you. I said 3 hours to do it, but you guys did it in an hour on average. So that's pretty good. So yeah. If you like the way the system's working, then I don't think I'll change it unless you guys want different types of tests. The problem with online classes and tests is like fidelity, and this is the program they gave me to kind of keep test fidelity. So that's why we're using it. All right, so let's just get into Unit 3, 7, 8, 9, chemical bonding, unless you have questions on anything we have done so far. Okay, so in the previous chapters, we've just kind of talked about elements. We talked about matter, we classified matter, we said what compounds were, we said that matter combines in set ratios, but now we need to learn about like why. Why is it doing that? Because if we understand why chemicals are bonding the way that they are, then we can hopefully make new compounds or design new compounds or understand ourselves better and just kind of understand how everything's coming together. So we're going to talk about chemical bonding for this unit and naming chemicals that have bonded together so that we know exactly what is inside them. So that's what chapter 7 is. It's all ionic bonding and metallic bonding, but we're not going to spend much of any time on metallic. And then chapter 8 is all covalent bonding, which is kind of, you know, the majority of bonding that you deal with in your life. And then we'll talk about how to name all that stuff in chapter 9. So chemical bonding. What's the point of chemical bonding? Well, what the heck is a chemical bond? Chemical bond is when atoms are mutually attracted to each other's electrons. But it's more important that we talk about a particular type of electron, and that is what's called the valence electron. The valence electrons are the outer S and P. We'll talk about types of bonds in a second, but I wanted to talk about valence electrons first. So when it comes to valence electrons, valence just means outside. So right here, valence just means outer electrons. So when you're thinking about the atom in terms of its electron clouds, right? Well, if you're an s orbital, like say you're just, you know, hydrogen, well then your electron cloud out here, you know, is 1s, and you have one electron in there. So that's going to be your valence electron because you only have one electron. But if you are, say, for instance, sodium, well, sodium has the 1s and then has the 2s, and then the final electron is out here in the 3s. So even though sodium has, you know, 11 electrons, there's 2 here and there's 8 here. Okay, and then there's 1 out here. So even though it has 11 electrons, this last electron right here is what we call the valence electron because it is the outside energy level electron. And when it comes to valence electrons, they're the S and the P's, the final S and P, and it has to do with the size of the orbitals. So remember the S is a big sphere, so the sphere kind of sticks out. And the P's were those dumbbells, and those dumbbells kind of stick out as well. The D and the F kind of like barely fit inside of the S's. So they just don't really stick out as well unless, for instance, you have like just the D's as the final orbital or just the F as the final orbital. So when it comes to the D and the F block, you'll notice when you look at here, when we're talking about things, we're going to be talking about the valence electrons in terms of just kind of the S and the P block, the A group, essentially. The B group, which consists of the transition metals and the intertransition metals, or the lanthanides and actinides, their valence electrons are difficult to kind of pin down as they're always 2, or they're always 1, or they're always 6. Sometimes it's 3, and sometimes it behaves like it's 2, and sometimes it's 2, and sometimes it behaves like it's 1, and so there's all of those. So we're not going to get too much into the D and the F block valence electrons. We're just going to know how many, we're just going to basically memorize their charges. By memorize, I mean you'll have a chart that I'll give you that'll show you all of their charges and whatnot. So if we look at the periodic table, then you'll notice, like in this thing, we are looking at the groups across the periodic table. Group 1A, their electron configurations all end in S1. That's what the N means. So 1S1 is hydrogen, and 2S1 is lithium, and 3S1 is sodium, potassium, rubidium, and cesium, and francium. are all S1. And then when you go to S2, you have, you know, the 2A elements, except for helium, which is moved over there. But either way, the same idea, you have S2. So beryllium, magnesium, calcium, strontium, those types of guys. And then all the 3A elements, which is the boron group, boron and aluminum, gallium, all those kinds of guys. And you have 4A, the carbon group. They all have 4 valence electrons, 5A, 5 valence electrons, 6A, 6, and 7A, 7. So that's kind of why when you look at the periodic table, you'll see that sometimes they're called group 1 through 18, and sometimes they're called groups 1A through 8A, and then they have the B. And that is because of the valence electrons. So the outer S and P valence electrons are the outer S and P electrons are called the valence electrons. And for some reason, when it comes to bonding, all these types of bonds here, ionic bonds, covalent bonds, metallic bonds, their whole point, the reason why bonding exists is for some reason, when it comes to energy, right? If we look at our energy diagram, when you are an atom, like say our sodium atom here, with its 11 electrons, it is very, very unhappy, sodium, as a 3s1 as its electron configuration. If we delete this 3s1 right here, then this becomes 1s2, 2s2, 2p6, which is 10 electrons, which is the electron configuration of neon. So by losing this one electron here, the sodium, which normally, you know, has 11 protons and 11 electrons, and normally is 0, if it loses this electron, it becomes positive and achieves the noble gas configuration of neon. And so when it comes to chemical bonding, the reason atoms are bonding is they're trying to achieve noble gas electron configurations. This is just the best way to arrange your electrons. And so if you're an atom, you're either going to try and lose electrons, or you're going to try and gain electrons in the form of ionic bonding. Or if you can't lose or gain because you're too weak to pull someone else's electrons off of them, then you can share to try and make it look like you have your full valence shell or a noble gas configuration, and that's what covalent bonding is. And then finally, metallic bonding is kind of the same idea with metals, where they kind of share their electrons and to achieve their noble gas configurations. So, and then polar and nonpolar is all about sharing equally or unequally. So today, we're going to talk about ions. And chapter 7 is all about ionic bonding and how ions form and what they're trying to do. So first off, we're going to talk about positive ions and why they form. And then we'll talk about negative ions and why they form. And then we'll talk about how things combine together. So in the previous module here, you got a periodic table, so we can use that. There it is. And so as we look at the periodic table here, if we look at our electron configurations, the noble gas configuration is the ideal. So all of these guys over here are one away from their electron configuration if they lose their electron. These guys are 2 away from their noble gas configuration if they lose their 2 electrons. These guys are 3 away. The carbon group is kind of the divide because it's 4. And so you could either gain or lose 4. And then finally, when we get here, if we lose 5 electrons, that's a lot of electrons to lose, and that's going to expose a lot of positive charge. So these guys begin to want to gain. And that's where there's that big divide between the metalloids, metals over here, and the nonmetals over here. It's caused by this switch from a desire to lose to a desire to gain. And some of the most reactive elements, fluorine here, is 1 electron away from becoming neon. So it's going to want to gain that electron very quickly and very violently. And then down here in the potassium, rubidium, cesium, those guys are very, very reactive too, because they are also 1 away, but they're 1 away and losing. So if we were to get some sodium and some chlorine together, well, that's the perfect storm, because sodium has 1 too many electrons than it wants, and chlorine has 1 too few electrons than it wants, and so they will exchange their electrons to become ions. When they do this, if they lose electrons, we call them cations. If they gain electrons, we call them anions. And that's because when ions were discovered, they were discovered using batteries, and so the positive end, cathode, the negative end, anode. So that's how that works. So anyway, positive ions are atoms that want to lose electrons so that they expose their valence shell underneath their outside energy level so that they can become the noble gas. These are usually metals. Metals tend to gain electrons to become their noble gas configuration. So it actually is pretty easy when it comes to knowing what group will do what. Just open it. I have too many photo things. So if you're in group 1, you have 1 valence electron, and so therefore you usually form positive 1. If you're in group 2, you have 2 valence electrons, so you usually form positive 2. The D and the F block have exceptions in there. Some of them make sense, some of them don't, so we're going to ignore the D and the F block for now. Group 3 has 3 valence electrons, so they usually form +3. Group 4 has 4 valence electrons, so it depends on the element. For carbon and silicon, they tend not to form ions. They tend to form covalent bonding, but if you can get them to form, a lot of the times they will form negative or positive. It depends on which atom you're talking about. Carbon tends to like to do negative. Silicon tends to like to do positive, but again, they don't tend to form ions. But germanium, tin, and lead, these guys are more metallic in their nature, and so they tend to form positive. But they can form both +4 and +2. So very interesting elements there. The nitrogen group now is at 5 valence electrons. And because they want 8, losing 5 is harder than gaining 3, so they're going to start to gain electrons. So these are now going to be our negatives. So this is -3 in this group. And again, antimony and bismuth are down in the metallic range, so they tend to do weird stuff. So, but again, they can do -3, but they like to do positive. All over the place. And then the oxygen group is -2 because they have 6 valence electrons right there. The Roman numeral is basically the number of valence electrons. We have 6 A is our group here, and so these guys are all 2 away from becoming their noble gases, so they're all going to gain 2. So we got +1, +2, +3, plus or -4, -3, -2, and then finally -1 for the halogens. The halogens all are S2P5 as their noble gas configuration, so they all want to gain 1 electron. And then finally, the noble gases are the noble gases because they are what everyone strives to be, so they just don't react very much. So positive ions are called cations, and negative ions are called anions. When you have 2 ions, it is not the exchange of the electrons that is the bond, it is the opposite charge. So let me show you. If we have our sodium here, okay, sodium. Sodium has 3 energy levels. I can't draw very well on this computer, I'm sorry. And we'll do electrons is green. So we have 2 electrons down here in the 1s, and then we have 8 electrons in the 2s and the 2p, giving us 10 total electrons. It is finally out here in the 3s1 that we have our last and our valence electron. If we look at chlorine, chlorine also has our 3 energy levels, right? Because it has 17 electrons. And so it still has the 2 here and the 8 here, like sodium does. But the difference between sodium and chlorine is that instead of having, we'll use blue, instead of having 1 valence electron, it has 7. So 1, 2, 3, 4, 5, 6, 7. So as you can see, there's a hole right there where we have a missing electron. They want to have 8 in their valence shell. Well, this guy is missing 1, and this guy has 1 too many. So if you get them near each other, they will exchange. And our electron will come over here. And this valence shell will go away. And what do you see that's underneath it? A full valence shell. So what happens is now, instead of 11 electrons, we have 10 electrons. We still have the 11 protons. And now, instead of 17 electrons, we have 18 electrons, but we still only have 17 protons. So this guy becomes positive, this guy becomes negative. Now, this is not an ionic bond. All we did was an exchange of electrons. An ionic bond occurs because now this whole thing right here is positive, and this whole thing right here is negative, and as we know, opposite charges attract. So it's what's called the electrostatic attraction of these 2 opposite charges that results in the ionic bond. They basically become the 2 sides of a magnet, and so they want to stick to each other. This makes ionic bonding very strong. One of the strongest amounts of energy in a bond are ionic bonds. However, because it is just simply an attraction of opposite charges, ionic bonds tend to have properties like being able to dissolve in water, because water is also fairly charged, and so rather than sodium and chlorine sticking together, they could also stick to the water. And so even though it takes a huge amount of energy to split the chlorine and the sodium apart, is say like heating it up, you can heat up salt for a very long time. It has a very, very high melting point. But if you took the salt and threw it in water, it would easily dissolve. So the whole point of coming together, though, as you can see, is that they're trying to neutralize each other's charges. They're going to stick to each other until eventually there's no charge left. And that is why the formula of a salt molecule, a sodium and chlorine molecule, is just NaCl, because they will combine so that their total charge equals 0. So properties, like I said, because they're so strong in attraction to each other, they tend to be solids. They tend to conduct electricity in water, which is what's called an electrolyte. They tend to have really high melting points, and they tend to be crystals. And because they're crystals, this means that they're hard and brittle. And, yeah. It depends on where you're coming from. Obviously, it says a demo here. I have a video that shows in the module, the video from Annenberg. So it's from Harvard, shows a really cool demonstration of the electrolyte properties. So go watch that video on that. Watching a video inside a video is usually not a good idea. So basically the idea is that if it's in solution, it will conduct electricity. But you can also use molten salt to conduct electricity as well, because that will also free up the ions and allow things to move around. When you're looking at the periodic table, if the cation, which is usually a metal, is in the S block or the P block, the salt tends to be white. And then if it's in the D or the F block, the salts tend to have a color. So a good example of this is rust. Rust is technically a salt. It is iron reacting with oxygen. Iron oxide is a reddish color. Iron, in this case, iron 3 oxide. You can also have iron 2 oxide, which is iron with a +2 and oxygen with a -2, and that is a black color. And then there are other iron oxides as well, but they all have some sort of color to them. Copper loves to form blues and greens. Cobalt is amazing with its blue colors. Chromium does green and purple, all kinds of really cool colors. Gold has this amazingly awesome orange color to it. And so there are lots of cool salts that can be made from the D and the F block with their very cool colors. And what we know is gemstones are usually some sort of salt that has some sort of metal contaminant in it that's giving it that really cool color. So for instance, your cell phone, the glass on it might be the salt aluminum oxide. Well, aluminum oxide is actually sapphires, but the sapphire blue color that you think of when you think of sapphires is either a cobalt or a copper contaminant in the actual aluminum oxide, which cause it to have that really cool blue color. So that just goes on to covalent bonding. So let's go ahead and look at how to form bonds by looking at their charges. What type of chemical will it form? And I'll post a table that will show all of your different charges on that. I have it in a file here, but I need to put it on your guys'. I need to put it up in a way that doesn't screw everything up. Oop, that's the wrong box. I want this one. All right. And then Either way, I'll find it for you, and then I'll put it up there for you guys to download. It's the ion chart. I wanted to add some stuff to it, so I'm finalizing it for you. So anyway, let's take a look at how things form. So whenever you're looking at an ion, and a cation or an anion or a positive or negative, you're going to combine them so that their charges equal 0. So for something simple like sodium with a plus and chlorine with a minus, they are going to combine together so that these things add up to 0. So +1 - 1 adds up to 0, so they're just going to be sodium chloride. Say, for instance, we have the next element, though, magnesium, which is right next to sodium. That's actually going to be a +2. Now, you'll notice when they write ions, they write the number, then the charge. And this is from old printing press days, but also there was a reason for it back in the day. It doesn't actually really matter. You might run into a professor in college that like fights you over the fact that this is correct and this isn't, but I don't care. Either way is fine. Yeah, so we have magnesium with its +2. If it hangs out with a chlorine, then the charges will not add up to 0 unless we have 2 of these guys. So what we're going to need to do is do magnesium, but now we write a little 2 down there in the subscript. Basically, a good way to do this is what's called crisscross, where basically the number of these things goes down here and the number of these things go down here. So 2 went down there and then 1 went down there. So let me show you that real quick with aluminum. Aluminum tends to be a positive ion. Oxygen is a -2 ion. So if we want to know what their combination will be, we can just simply take the 2 and take the 3 and we'll get aluminum oxide. And you'll notice that this will add up to 0, because if I multiply this by 2, that gives me +6, and if I multiply this by 3, that gives me -6. So remember, ionic compounds are combining together to form a formula, and that formula's charge needs to add up to 0. So now I wanted to talk real quick about the D and the F block, because the reason why we don't really want to look at their valence electrons is because they do more than one thing. So a great example of this is iron. Iron in our blood is the very important thing at the center of the hemoglobin molecule in our red blood cells that transfers oxygen throughout our body. Well, the reason why iron can do this is because iron has what we call 2 different oxidation states. Oxidation state is just another way of saying charge. When they would find the charges of things, they would react them with oxygen, and that's why they call charge oxidation state. So anyway, the iron, even though if we look at its electron configuration, it has S, in this case, iron would be 4s2, 3d6. It sometimes behaves like it has 2 valence electrons and it wants to lose those electrons to become iron +2, but it also behaves like it has 3 valence electrons to become iron +3. So it has 2 oxidation states. We call this guy iron with a Roman numeral 2, and we call this guy iron with a Roman numeral 3. So you need to look at the particular iron that they're talking about in the example to be able to know how to balance it. But like I said earlier, when we're talking about oxygens, say iron reacts with oxygen, well, 2 iron oxides can form. Iron is very reactive with oxygen. So normally what will happen is that you'll get the formation of iron 3 oxide. And so what we do is we use our crisscross method and we get Fe2O3. And this is what we know as rust. That's what most of the time happens. But in this case, we can do the crisscross method as well. But when it comes to ionic compounds, we don't want to put the 2's there. We want the absolute simplest ratio. So if you're doing an ionic compound and it says 2 and 2 or 3 and 3 or 4 and 4, you just want to simplify that to 1 and 1. And this right here is what we call ferrite. And it's in computers. It's used for voltage regulation. So these are our two types of iron. This one's called iron 2 oxide. This one's called iron 3 oxide. But again, I just wanted to show you that if you're looking at your work today and it says that you have two different irons or two different cobalts or two different whatevers, that's why. They will behave like they have multiple charges. If you'd like to know why iron does that, then we can talk about it, but it's not that important for this class. So yeah, if you're going through the classwork today and you're forming ions, like say right here in the sample problems, when it has you start mixing stuff together down here in the bonding, it says, okay, use the electron dot structures to formulate the compound. Okay, so they want you to talk about, I'll show you the dot structures in a second. And then metallic bonds, we're going to talk about right now. That's what you want to do. So anyway, what is an electron dot structure? Lewis dot diagram. So it's just a way to do the valence electrons with simple, easy dots. So instead of hydrogen being 1s1 as its valence, writing it to understand what type of electrons it's going to lose, we just draw a dot. And instead of helium being 1s2, we just draw 2 dots. And notice how we draw them together. Because what this is showing us is that this guy has an empty spot for an electron, and this guy does not. When we go to lithium, lithium has 1s2, 2s1, but this guy is our valence electron. So instead of drawing these guys, we just ignore them and we just draw the 1 dot. Beryllium, same thing. But now we're going to draw 2 dots, and we're going to draw them on opposite sides, because what this is showing us is that we have space for more bonding. Then we have boron with its 3 dots. Then we have carbon with its 4 dots. And then we have nitrogen with 5. So we draw it like that. And then we have oxygen with its 6. We draw it like that. And then we have fluorine with its 7. So we draw it like that. And so what you can see is how the thing will bond. In this case, the lithium has 1 electron, beryllium has 2, boron has 3. So these guys are all going to want to lose their electrons to get to their noble gas below them. And that's why lithium loves to form +1. This guy forms +2. This guy forms +3. And that's why carbon and silicon are an exception. You can see that they have 4 spots they need to fill. They could either kick out their 4 electrons, or they could try and gain their 4 electrons. And that's why we usually call these guys +or -4. As you can see with nitrogen, losing 5 electrons would be a pain. So gaining 3 would be better. So these guys tend to form -3. I need to draw 3. These guys have 2 spots that they would like to fill, so they tend to do -2. And this guy has 1 electron that likes to fill, so it tends to do -1. So when it comes to doing dot diagrams, it's actually pretty easy. We can use the Roman numeral again to show how many dots. Everything in group 1A, right, will have 1 dot. So, and you can put this dot anywhere around the symbol. So potassium, 1 dot, and rubidium, 1 dot, and cesium, 1 dot. Oops, that's not C. These guys are all, and I'll just put the dot over here to show you can put it wherever. They're all in 1A, so therefore they have 1 dot because they have 1 valence electron. Helium's over here. Helium's an exception. It has 2 dots. We put them right there. So then we have beryllium, and we have magnesium, and we have calcium, and we have, I think, strontium. I'll just do the 3 right there. And these guys are all our 2A, and so therefore they all have 2 dots. And we're going to put them on different sides of each other, because what this is going to show us is that those are the valence electrons. Those are the reacting electrons. And then if we go over here to the 3A group, that's going to be our boron and our aluminum and our gallium or germanium. Which one? Gallium. Okay. That's what I thought, but I'm silly. Gallium. Yeah. It was strontium. I'm so silly. Boop. There we go. And so these guys all have 3 electrons. And again, you can draw them anywhere around them as long as you draw them kind of away from each other. Our 4A group all has 4 dots each. So silicone, these guys are all going to behave the same way. And then this is germanium right here. So they're all going to be exactly the same because they all have 4 dots and they're going to spread out around it. Our 5A electrons are going to be our nitrogen group. And so we have nitrogen, phosphorus, and arsenic. And these guys are all going to have 5 dots. So 1, 2, 3, 4. And where you put the 5th dot is what's going to lead us into what we call our paired electrons. So in this case, we have what we call a lone pair. They're called lone pairs because they are paired up already, and so they're not available for bonding, and so we call those lone pairs. And so now we have 3 electrons here around the arsenic that need to have a partner, and so that's why these guys tend to want to form the negatives. So now these guys will always form -3. For our 6A, that's going to be our oxygen, our sulfur, and I'm trying to remember off the top of my head, selenium. Selenium, and then we have our 7A, which is going to be fluorine, chlorine, and bromine. And these guys are going to be 1, 2, 3, 4, 5, 6. Or 1, 2, 3, 4, 5, 6. Or 1, 2, 3, 4, 5, 6. All of those are perfectly fine. And because they have 2 spots left over, they tend to form -2. And then with the fluorine group, we have 1, 2, 3, 4, 5, 6, 7. Or 1, 2, 3, 4, 5, 6, 7. Or 1, 2, 3, 4, 5, 6, 7. Those are all fine. And that's why they tend to form -1. So these are the Lewis dot structures. When it comes to the D or the F block, it's kind of hard to write Lewis dot structures for them. For instance, in iron, when we were talking about iron, is iron 2 valence electrons, or is iron behaving like it has 3 valence electrons? And the answer is it depends on the particular reaction. So we don't tend to like to draw dot structures for the D and the F block, and I won't ask you to do that, so don't worry about it. We spend more of our time with our Lewis dots with covalent bonding than we do with ionic. ionic. We're more just interested in group 1 is +1, group 2 is +2, group 3 is +3, 4 is +4, -4, -3, -2, -1. So, and then the noble gases, group 8A, they are all the noble gases because they are completely full. So krypton, xenon, all those guys are exactly the same, and that's because they have 8. So they have the 4 dots around it. So 1, 2, 3, 4, 5, 6, 7, 8. So these are Lewis dot structures. And if you want on here, if you want to print this out, it's up to you. I usually, this is a digital class, so maybe you're using it digitally. You can have that on there. But you can also look at any other periodic table, and sometimes they'll have that, and then you can download that if you want. If you just took dot structures, if you want to see that, and if you do images, chances are you'll find a periodic table that will show you all of the dot structures that are on there. Here's a good example of electron dot diagrams using the S and the P block. Most of the time you'll see, if you look at dot structures, they will leave out the D and the F block because, again, they do multiple things. So yeah, lots of different ways to look at those. If you want to just do a periodic table, the one I provided you doesn't have the charges on it, but you can obviously find another periodic table that will show you the charges on there. Some are more elaborate than others, depending on what it is they're trying to show you. In most textbooks now, because we're looking at new textbooks for all the schools because of the NGSS stuff, you'll notice that they will sometimes even show you the charge, but also provide for you the electron configuration, like right onto the table. So this one's not an example of that, but either way, lots of different periodic tables for you to look at if you don't like the one I provided for you. Your book, I believe, has a decent periodic table in it as well. And then, of course, the periodic tables that are in chapter 6 and 4, I think, has them as well. Are pretty good. You can just type charge. I did chart. Charges. So then you can have a periodic table that like shows you all the charges that they would have. Science notes. So there you go. You can see that this will have all these guys are +1, all these guys are +2, and then when the D and the F block comes in, you'll see that some of them only have one charge that makes sense, like +3, +4, +5, but then sometimes you have +3 in there, and then iron with its +3 and +2, and then the same thing goes over here. You should see, -3, -2, -1, but then you can also see some other weird stuff that's going on. But either way, you can look at that to help you out. So that's chemical bonding, ionic bonding. That's pretty much all you need to know for most of chapter 7 to get through everything. The metallic bonding stuff here at the bottom, we're not going to do very much with metallic bonding. So basically, I just want you to know what metallic bonding is. Basically, metals tend to form when the metals get together, they tend to form this big like pool of electrons, which we usually call what's called a delocalized sea of electrons. And this tends to cause the metals to be very conductive and to be very malleable and to have high melting points. Metallic bonds tend to be strong, but I'm not going to ask any questions on the test for metallic bonding. I'm not going to make you understand, to memorize all that kind of stuff, because there's too many exceptions to the way that metals kind of bounce around. So we're not going to concentrate too much on metals. I just put it in there for your reading if you were interested in how ionic is different than metals. So even though they have similar properties in some instances, how they're crystals and they tend to be conductive and all that kind of stuff. But metals don't dissolve in water and they have very different reactivities and all that kind of stuff. So that is pretty much today's discussion. Any questions? Okie doke. So I'm going to stop the recording.